Check. Check, check. Oh. Should we give it a minute? Yeah. Any of your friends around you who haven't seen them, call them. The last class, trust me, it will be entertaining. Okay. So if you see your friends who are not around you, just call them and make sure that they're here. We'll start in a minute. Sorry? Sure, sure. You don't have to tell me. It's okay. I'll trust you'll come back. Okay, so I think it's a minute past 2, so let's get going. Thank you all for coming. This is the last session between you and the exam. So I'll try to make sure that I don't give you too many new things to learn, but I'll be talking about one of the most rapidly evolving part of compiler technology, which some of which was talked about in the morning, but we'll talk a little bit more on the programming language side in my lecture. and then we'll do some hands-on exercises. So before I get going, first want to thank Krishna for inviting me here. My name is Pradeep. We also have Arjun, who's the TA for the class. He'll be around in the after, he'll do the section after mine. So the title for what I picked, initially I'd given Krishna block-based programming for GPUs, but then as I started preparing, I figured that it made sense to not just talk about block-based programming for GPUs, but how GPUs get programmed in general, and do a lot more about block-based programming, and the tutorial will focus a lot more on one particular block-based programming language. But before I get going, I thought it's useful to know where I come from, what my background is, because you're listening to me and you're wondering who's this guy, right? So just a quick background of myself. So I'm from Chennai. I graduated from IIT Madras, and I got my PhD in the US. I worked across multiple research labs, across designing hardware in Intel, building compression algorithms in a couple of small companies. I joined KLA, where I work today, in 2021 to start what's called the Advanced Computing Lab, based out of the IIT Madras Research Park. So the focus of my lab really is looking at hardware-software co-optimization of computer vision problems for solving problems in semiconductor manufacturing. It's a lot of words. If you're curious what I do, I'm happy to talk to you offline. I'm not going to be talking about that today. But the essence of my work really is trying to figure out how to make sense, like that gentleman in that picture, of AI and hardware. We look at it as a whole system. We don't think of it as two separate problems. In the morning, the lecturer spoke about co-optimization. We really take it to the extreme, right? So we look at large systems that are a lot of GPUs running large models, ChatGPT, like GPT-5, big models, computer vision problems, trying to make sense of it. That's what I do. So a lot of the work that I'm going to be talking about here is not, of course, not based on anything that we do at KLA. I have to say that for legal reasons, right? So this is a lecture giving you an insight as to what actually happens in this space. Okay, so couple of housekeeping things. I have a bunch of chocolates here. Okay, so I'll ask a few questions. If you have an answer, feel free to shoot up. You get a chocolate. I have a lot of chocolates. I'm the last session. Whoever is the most talkative gets the most chocolates in the end. I give the whole bag to that person. Okay, I know it's just after lunch. Probably the cold AC is making us a little drowsy. So it'll be nice if everybody is interactive. Feel free to stop me at any point and ask me any questions about GPUs, AI, and programming. Okay, if it's sort of related to what I'm talking about, it's better. It doesn't have to be. Okay, and you can bug Arjun the same way as well. I'm sure he wouldn't mind. Okay, any questions before I get going? First chocolate? Nobody? Okay, let's get going. So, why are we talking about GPUs, right? We're talking about GPUs because GPUs really started or enabled the AI revolution. How many of you know about AlexNet? Somebody? What is AlexNet? No, Arjun, don't answer. Anybody else? Anybody heard of AlexNet? Take a guess. What is AlexNet? It's a CNN detection algorithm. Good. Here's a chocolate for you. Anybody else? Good sugar after lunch. Anybody else? Take a guess. So in the 2010, about from 2008 onwards, there was a big problem called the ImageNet problem. Anybody heard of ImageNet? ImageNet is a big data set that's used for, it has millions of images. It's basically a data set that has a lot of images collected from all over. And the challenge basically was, can you write a piece of software to find the images? Can you find objects in the image? And the most popular objects to find were cats and dogs. Don't ask me why, but somehow people really seem to want to find cats and dogs. But the biggest problem, most of the images are cats and dogs, but there are also animals, vehicles, houses, things like that, right? So the ImageNet problem was one of the largest problems in computer vision. And circa 2012, if I remember, it's 2012, this ImageNet problem was floated by Fei-Fei Li, who is today known as the mother of data, a woman researcher, right? So Fei-Fei Li's ImageNet problem, AlexNet in 2012 came and blew it out of the water. It beat the next problem by more than 2x in terms of accuracy, by more than 2x. Until then, everybody was getting 5%, 3%, 4%. This guy got 100% improvement. And the way they did it was using this network, which was CNN based, as he rightly said, trained it on GPUs. Until then, the biggest limitation for computer vision was the fact that there was not enough compute to run big computations. And the success of ImageNet was because it was trained on that GPU. Anybody recognize what the GPU is? It's on the slide. Titan, who makes that GPU? Alright, you get a chocolate. It's an NVIDIA Titan GPU, right? So it was programmed in the programming language called CUDA, which I'll tell you a little bit about. But in a sense, 2012 really is when the AI revolution started, right? And that has continued over the last, I don't know, 10 years, 15 years now, because the GPUs continue to sustain the AI revolution. So if you look at this graph is showing you on the y-axis the tera operations per second, right? Think of it as how much is 1 terabyte? So gigas 10 to the 6, 9, okay, you get a chocolate. Tera is another chocolate up for grabs. He said it, sorry. Very truthful man, I like it. Tera, so what is tera? If gigas 10 to the 9, 10 to the 12, she gave me a 12. So 10 to the 12 operations per second. On the x-axis is time, and as you progress through time, it's showing you how the flops on the NVIDIA GPU have been improving. I mean, NVIDIA has of course been a driver in the revolution. And literally over the last 10 years, performance has gone up by 1000x. That's 100x performance every year, right? And ironically enough, the demand of AI is more than what this actually is. The demand of AI is more like 1000x every year. But we are at least able to get what we are able to get because of the GPU. So GPUs have really sustained their evolution. Now, this is pretty obvious to a lot of you, right? All of you are working, wondering, what is this guy talking about? I know all this. Where is the compiler coming? It's coming. Right? So I thought it will be good to set this up because now you know why it's very important to have good compilers for GPUs. Because GPUs have enabled the AI revolution. They enable you to sustain the AI revolution. And if you don't have good compilers for GPUs, it's a big problem. And having compilers for GPUs is a very, very unique problem because AI is programmed in languages like Python and C++ using multi-dimensional arrays, which are also called tensors. I mean, tensor is just a fancy word for a multi-dimensional array. But traditional compilers, LLVM, GCC, were only good at doing scalar operations. So all the people optimizations you studied, SSA, who can give me a, what does SSA stand for? Okay, no chocolates, everybody answered. Very good, I'm very happy. Right? Static single assignment, right? So SSA as a concept assumes that each element that you're assigning to is a scalar. LLVM fundamentally does not have a vector allocation. They've added vectors recently, but at the fundamental level, LLVM when it started did not have vectors in it. It's obviously a mismatch right here. Because here you're not just talking about a vector, you're not just talking about a matrix, you're talking about a multi-dimensional matrix. And these matrices grow in thousands of orders of dimension. It's called ranks. And the vector just, LLVM, which is even today the most popular compilation framework, does not understand vectors and matrices fundamentally. So it's a big problem. The person who's been coming to the rescue is MLIR, which is what the lecture in the morning was about. Right? So what MLIR does is understanding that at the lowest level, which is LLVM, you only know scalars. However, at the highest level, whether it be TensorFlow, PyTorch, Python, whatever you have multi-dimensional tensors. So in MLIR, what you do is you go through what's called progressive lowering, where you start, essentially if you think about it, a multi-dimensional tensor is composed of a bunch of scalars. Each element is a scalar. But if you look at a matrix multiply, in scalars, it looks like a triply nested for loop, right? Anybody dares tell me you get 2 chocolates? How to write a matrix multiply for loop? So 3 or 2? 3? You want to tell me what a matrix multiply will look like? You want to come and write it? Sure? Yeah? Yeah, just write it big. Just write the for loops, right? Just the big for loop. Big font. I want the guy in the last row to be able to see it. Big font. So you have an I loop. You have a J loop. You have a K loop. And just write one operation, right? What is one operation? C of ij equals plus equals A of ik plus B of kj. I know I dictated the answer, but he had the guts to come up and do this, right? So yes, he gets to. That's cool. Yeah, thank you. So that's the triply nested for loop, right? So at a compiler level, when you're in LLVM, you just see a C of ij equals B of kj or A of ik plus B of kj, right? For you to be able to infer that this is a for loop with 3 loop nests, it's a very non-trivial problem. So what that boils down to is the fact that at the LLVM level, the semantics that this add operation is for a matrix multiply is completely lost. Why? Because all you're dealing with is scalar operations. You don't know anything about a vector, you don't know a matrix, you don't know this is a matrix, you don't need to try to do a matmul. Right? See the problem? So what MLIR does is at intermediate, like linealg is one of the dialects in MLIR. A dialect is just another IR, another intermediate representation. At dialects that are closer to the top, there's more semantic information about the program. You know what's a loop, you know that this is a loop nest, you know what the indices are, you know the data type of the indices, etc. etc. At dialects closer to the hardware, you know more information about the hardware. Like for example, you know what the cache size is. Therefore, you do tiling. Who can tell you what tiling is? Very good. Breaking down a large matrix into a bunch of smaller tiles so that it fits in the cache. That's the fundamental thing, right? You want to fit it in the cache. So when you go closer to the lower levels of MLIR, you get more hardware aware. When you're closer to the top, you become more application aware. So the fundamental idea of MLIR is the idea of progressive lowering, and at each step you can do optimizations. Can somebody tell me a good optimization for this triply nested for loop for 3 chocolates? Vectorization. Vectorization is one step afterward. Okay, I'll give you a hint. Okay, let's say that you guys know what a row major order, column major order is. I think that was covered in class, right? Assuming that all arrays are row major ordered, give me a good optimization for a triply nested vector or for a matrix multiply that gives you good performance. Unroll. Unroll can be used for anything. I'm giving you row major order. That's my hint. Excellent. You can transpose the second matrix or you can interchange the loops. Right? You interchange the J, I got 3 chocolates for you. Interchange the J and the K loops, you actually get a lot more power, just free performance, and there's no loop carry dependence, so you can actually do it for free. Right? And this kind of optimization is impossible to figure out at LLVM level. Right? You have no idea that this thing is a triply nested for loop, there's a loop carry dependence across 3 loops, really difficult to get. Polyhedral compilers, which was mentioned in the morning, does analysis of loops, and the linealg dialect is all about polyhedral compilers. So because you know that this is a loop, you know that this is a matrix, you're trying to optimize, you can do a lot better. So MLIR is fantastic, right? It's a great invention, it's been going really well. But this is what the real world of dialects looks like. What I showed you earlier was like a very small subset of just one operation. Right here on top are PyTorch, TensorFlow, and something called TF Lite, which is used for deploying on edge devices. Right here on the bottom is LLVM. This looks like traffic outside SRM college, right? It's a very non-trivial amount of paths for you to take. How do you figure out where to go? Right? So LLVM is a beautiful framework, it's a fantastic infrastructure, but like most compilers, it's not easy to navigate. It really takes a lot to build a programming language, to build a compiler for a parallel programming language. It's very difficult. I mean, I've been a computer science student for a long time, right? And the promise of parallelizing compilers has been there forever. I still remember classes where they said parallelizing compilers will come in the next 5 years. It's been 25 years since, and still that 5 year keeps getting pushed out, right? But MLIR is honestly one of the best inventions that I've seen, which is the most promising. The idea of parallelizing compilers is really looking, right? But the problem and the reality today, and the gentleman in the morning will also agree that auto-generated code for GPUs still is lacking. Compared to existing compilers, MLIR based compilers are fantastic. They get really good gains. The main place where they get gains is that they are able to leverage, like I said, semantic information. What is semantic information? You know that you are a loop. You know this is the loop carry dependence. You know that this is an n-dimensional vector or an n-dimensional tensor or it's a tensor n-dimensional matrix. You know it's a vector. You know it's a sparse vector. All that information is available with the programmer. You give it to the compiler, MLIR does a great job. However, this is a blog by this person called Chris Lackner, who is the father of LLVM. He started LLVM as a PhD thesis. He also started MLIR, right? Chris, in some way, concedes and says that today, despite 8 years since LLVM started, since MLIR started in 2018. It's 2006 as of next week. By then, the course will be over, right? It's he concedes that MLIR based compilers is there's still maturity to be had. 8 years on, compilers is a big problem, right? Qualcomm has 50 people as a compiler team. Compiler is not easy to build. So it's evolving. It's a great place to it's a very fast evolving land. It's a very nice tutorial, very nice blog post. It's a series of blog posts from Chris's company called Modular. There's a link. You'll get the slides. It's a beautiful blog post. 6 blog posts about what it takes to write compilers for GPUs. Right? I strongly encourage you to go and see this. So what is the alternative, right? What is the alternative? Which means that MLR compiler is not ready, but GPUs are necessary. Why? Because I want to do ChatGPT, right? I want to ask, where is the cat and dog? So I still want to use AI. So we need to be able to use the GPU. So what's the problem? What's the other way? The other way to date is programming in a language called CUDA. How many of you here know what CUDA is? Can somebody take a crack? What is CUDA? Device architecture. Very good. Chocolate. So CUDA stands for Computer Unified Device Architecture. CUDA was invented by, can you pass it along? Careful. Yeah. So CUDA was invented by NVIDIA. It was introduced by NVIDIA in 2006. And the reason why CUDA was invented is because compilers were not mature for GPUs. Ironically, 20 years hence, I can still say the same line. It's not yet mature, right? It's hard. It's a hard problem. It's not easy. We have the best brains in the world working on it. It's not an easy problem. The beauty with CUDA is that CUDA put the power of the hardware in the hands of the programmer. The programmer, I'll show you some examples. For those of you who have not seen CUDA, you'll really understand what this means. But it resulted in the growth of what's called a ninja programmer. A ninja programmer is somebody who understands hardware. All of you will become ninja programmers when you take up systems courses. You write software understanding what the hardware is doing. You don't write software thinking, I don't care where it runs. I just want it to work. Which is very fair. I mean, there's a whole gang of engineers who do that, right? All your AI engineers mostly are like that. Unfortunately, AI engineers are mostly like that. They just want it to run. They don't want to think about money. They don't want to think about cost. They just want to say, my model has to run. I don't care if you have to spend the money, get my model to run, give me output, right? But the ninja programmer understands what the hardware is, understands the capabilities and limitations of the hardware, and writes software, like for example, the loop interchange is a very good example, right? Simple operation, but you know that it's a row major ordered matrix. So you loop interchange. That resulted in Ninja programmer. So I'm going to show you a very simple code in CUDA. I haven't compiled this. I don't think there's a bug, but if there is, please tell me. I'll fix it later. But it's a very simple example I'll show you. Left side, simple C++, hello world, right? Printf, hello world, return 0. On the right side is the equivalent GPU code. I'll just quickly walk you through it. Ignore this for now, or let's talk about this. So this is a function, void GPU print. It just calls printf hello world. In front of it, there's a special directive called __ global __. It's 2 underscores there. That directive indicates to the CUDA compiler that this is a GPU kernel, meaning though it's in the same CPP file, it will execute on the GPU. Anything that does not have the __ global __, or there's another one called device, anything that don't have that directives runs on the CPU like a regular code, right? So on the CPU you have main, run int main. Now you have this new unique syntax, right, where you're calling the function. You call the kernel like you call a function. You call GPU print. You give a bunch of parameters in triple angular braces, and you pass any function, any parameters that the function wants. Here the function takes no param, so it's easy. What does this mean? This means that 5 into 1024, about 5000 threads, will execute that function in parallel. Rather, each of the 5000 threads will run GPU print. There are 5000 threads that will run GPU print at the same time. This ran a single thread of hello world. Very simple change gives you 5000 threads of hello world running from the same program. Are you with me? Any questions? It's pretty powerful, right? Seems like such a simple programming model. The programming model is so intuitive. The function is a linear function written exactly like what you write in C++. It is C++. It's called CUDA C++. Except with this special primitive, it runs on the GPU, right? And you invoke it using this triple angular braces. Let's not get into why 5, 1024. Let's ignore that for a second. But 5 into 1024 threads launch and they all run in parallel. Got 5000 GPU cores just boom firing on. It's so powerful. What's the problem? Anybody wants to guess what the problem is? Why will the words come out all jumbled? Very good. You already got 3 chocolates. I'm going to give you a chocolate. Okay. So, but he's right. See, if you notice, there's no synchronization between the threads. Right. So, all threads run in parallel. So, if you look on the screen, you'll see H, E, W, sometimes hello world. All 5000 will print on screen together. So, CUDA also obviously has constructs of synchronization that enable you to actually synchronize the programs. I have not shown it here for simplicity. But as a programming model, you now start to understand. As a programmer, you now have to think, okay, what's running on CPU, what's running on GPU. You know that there's a GPU, which itself for a lot of people is a leap of faith. Then you have to think about synchronization so that you get right correctness because all these threads are running in parallel. So the Ninja programmer is responsible to do this. But as a programming model, it's very powerful. However, if you look at what CUDA is today, as NVIDIA advertises it, anything under the applications, anything under PyTorch or ONNX or TensorFlow, and anything above the OS is all called CUDA today. It's all CUDA, right? Starting with the language itself, but it's like a little small. You see this CUDA C++ core? That's all I showed you earlier, right? Today, CUDA encompasses the compiler, the toolkits, the driver, a lot of libraries for machine learning, HPC, extensions to languages is all cumulatively called by NVIDIA as CUDA. In fact, ironically, NVIDIA, which makes all its money by selling hardware, has more software engineers than hardware engineers. But they don't make a single dollar out of software. Because this piece of software called CUDA enables unlocking the power of the GPU, which today drives the AI revolution. But I'm talking about CUDA from the traditional sense of CUDA, which is your CUDA C++ core, which is the language itself. Right? So CUDA was very powerful as a programming language, very powerful, unlocked the GPU, enabled a lot of performance. But in my opinion, it's one of the biggest nightmares of a programmer. Because suddenly, as a software programmer, I need to think about hardware. I don't want to do this. Right? I'm a software programmer. I chose to do web application development. I chose to do AI. Now you suddenly tell me I have to go take a compilers class, go take a systems class, go take a hardware class, go take an architecture class, understand what it is, figure out threads, figure out programming. Very non-trivial. Broke one of the fundamental ethos of abstraction that computer science teaches you. So, big problem. Another big problem, CUDA is not portable. CUDA is designed for NVIDIA GPUs, deliberately for a reason. NVIDIA wants you to buy their GPUs, of course. But it's a problem because when you want to change the GPU, even within NVIDIA from one generation to another, functionally it ports, performance does not port. So that's a problem because I suddenly bought a GPU for $10,000 and it doesn't work or it's very slow, which means I have to sit and rewrite all my application, which means I have to learn a new architecture, I have to do all the synchronization again. It's a very non-trivial problem. So CUDA being non-portable is a big problem with the architecture. But again, I reiterate this, right? 2006 when CUDA 1.0 was introduced, it was then the best solution. Today, 2006, 2005 December, 2006, let's take leap of faith that we will go through into the new year. It still is the best programming language for the GPU. In fact, it's so good that every GPU that releases has its own programming language, which is very similar to CUDA. From a programming perspective, they all are very similar. It's another mini-me of CUDA. HIP, which is used for AMD GPU, DPC++ used for Intel GPU, all very, very similar. But this is not easy. Let's take this example, right? So this is matmul in PyTorch. Beautiful, so simple. Def matmul a comma b, return a b, done. That's the CUDA equivalent. Somebody wants to write on the blackboard? I'm not going to do it. Arjun maybe? I don't think so, right? This is actually the CUDA functioning equivalent work of the matmul. And I can give you the code offline if you want to look at it. But imagine writing this code, imagine yourself debugging this code, or a company like KLA, where what we do is we sell machines that are used in semiconductor chip manufacturing, and the machine lives for 25 years. Imagine that, I ship this code, I don't work for KLA anymore, somebody else comes in 20 years later, has to fix a bug in this code, it's going to pull hair out, there's no way, right? So from a maintainer's perspective, it's a nightmare. Right? You get it once, it compiles, you ship it and pray to God you don't get a bug again. It's really hard because getting it right, getting it performant is a very, very non-trivial problem. It works, it's fantastic, it gives you great performance, but maintainability is a big problem. Right? So what are alternatives? Finally come to the start of my lecture, right? Half an hour in. The two main alternatives that come instead of relying fully on the compiler going all the way low level, let's go midpoint. A lot of the hardware vendors actually release high performance libraries which can be used directly. That's one very powerful way to program GPUs. I'll talk briefly about that. But where I'll spend a bulk of my time on, and that will lead me towards block based programming, is languages like C++ and Python have also been evolving to support programming the GPU. Right? So focus of this lecture will really be to give you a flavor of both of these, and like I said, it's an extremely fast moving world. Right? Every day, every week, there are multiple papers, multiple languages being released that address different challenges in this trade-off. Right? My lecture is full of references to fairly new material, most of which are YouTube videos. It's not even published papers and all of this right now. Certainly not stood the test of time because most of them are less than 3 years old. But it's such a fast-moving field that that's the best way to learn. So I strongly encourage afterward seeing some of the videos that are there. I cannot tell you if I will not ask questions from that in the quiz tomorrow. Okay? I want to leave this on. Any questions before I dive into these? While I take a sip of water. Okay, good. So question is, what about more general purpose frameworks like OpenACC and OpenMP? They don't come close to CUDA. They're not even close. From a performance perspective, they're not even close. So some of the angles where performance is maturing is indeed adding these pragmas. OpenMP has a bunch of pragmas you can add to C++. From a community perspective, it's not being looked at as that forward. The scientific community, which is more HPC, has been using that for a long time. But the AI community is not able to use it because some of the parallelism constructs that come in AI are a lot less structured than that come in scientific computing. Scientific computing is much more structured, right? It's a small grid, rinse and repeat millions of times. AI is not that way. I mean, think of your AlexNet. Each layer is very different. And maybe you get 10 instances of one layer, right? Of one particular type of operation. Then suddenly you go from convolutions to matmul to attention block to bias to ReLU. It's completely different, right? So those pragmas are not, we don't see it scaling as much for the more modern workloads. Yeah, good. Thank you for the question. Any other questions? Fantastic. Okay. Sorry for that. I don't know why that. Anyway, so let's talk briefly about the device libraries that the vendors actually provide. Right. So what accelerator vendors actually do is they take their Ninja programmers and they build libraries for high performance versions of all your popular functions, whether it be image processing, math. In turn, effectively are written using hand-tuned CUDA, except that they're provided as a nice abstraction, so you can call the function directly instead of actually sitting and writing hand-tuned CUDA. In fact, the irony is that it's so good that modern compilers call into those libraries instead of generating code. So all of what you learned in the last 10 days are actually not used to generate code for GPUs. It's irony, right? It's very sad, but that's the difficulty of generating code for this beast, right? Most of the libraries, whether it be XL8, TVM, or what are the others? Those are the two probably most popular compilers that are available for AI today. most of them actually call into these hand-tuned libraries instead of native code generation. MLIR is evolving for certain very regular structured operations like MATML. MLIR starting to get used, but otherwise best performance comes out of hand tuning most of these, and the device vendor providing these libraries enables you to directly get it instead of actually compiling, instead of actually handwriting them. And the good thing also is that these device libraries, which earlier were only available for C++, are today also available for Python. So if you're a Python programmer, you can actually call directly into these libraries. So if you want to go and write GPU code, don't build a compiler first, don't go and learn CUDA first, go and look at these libraries as the first thing to do. So on the left side are the bunch of families of libraries that are developed by NVIDIA for NVIDIA GPUs, and on the right side an equivalent for AMD GPUs. I'll just call into a few of them. I'm not going to go into all of these, but these are popularly used routines in many fields. cuBLAS, basic linear algebra. All your solvers of all kinds are all available in cuBLAS. cuFFT, if you want to do fast Fourier, very common when you want to move from pixel plane to frequency plane in image. When you do a Fourier transformation, cuFFT optimized, beautiful library. It works really, really well. Excuse me. cuDNN, all your popular deep learning neural networks, convolutions, MATML, bias, convolutions with bias, convolutions with ReLU, convolution with tanh, all kinds of operations, optimized for different sizes and shapes, all available in cuDNN. cuLitho is something that we as people who work in the lithography or the manufacturing industry use. Common functions used in manufacturing which are required to run on GPU are implemented over here. What are the others? NCCL, communication libraries, right? NVIDIA complex communication libraries, NCCL, very good primitives, all GPU to GPU communication. Now, so think about it, right? Even the communication kernels are hand tuned. That's the power of CUDA. That's the kind of performance that you can get. So, like I said, everything that you see here is library functions available to program the GPU. Your compiler is also targeted, and as a programmer, you can find maybe a better fit sometimes than what the compiler can fit. So, this is a great way to start. An equivalent is also available in AMD. I'm not going to talk about too much, but you can see, right? Names are fairly similar and intuitive. HIP BLAS, everything that's CUDA in NVIDIA is HIP in AMD. So, Cu gets replaced by HIP. So, it's a HIP FFT, HIP BLAS, there's a HIP DNN, something that you can find the equivalent. So, that's the idea, right? So, this is one powerful way to program GPUs. I know standing in a compiler class and telling you to use libraries is not the right thing to do, but this is the practical way that GPUs actually get programmed today. Yeah. So, the next alternative is to actually leverage advancements in high level languages like C++ and Python that express parallelism better. I'll spend the bulk of my time talking about this in the afternoon. So, let's start with C++. Right, C++ has been a very powerful language. It's been around for a very long time, built on top of C, right? But starting C++ 11, where they started doing a regular cadence of C++ every 3 years, parallelism has been imbibed into C++ with a compiler behind it generating performant parallel code for a long time. It started with the introduction of a new memory model in C++ 11. Threads became a fundamental construct when you're actually programming in C++ 11. Scoped locks also became useful. C++ 17 introduced one of the most powerful abstractions called parallel STL, where in a standard template library function, whether it be a std sort, whatever algorithm you use, you can actually get parallel versions. I'll talk a little bit more about that in this slide. And then with C++ 23, there's also a notion of what's called a std future, where you can do what's called an asynchronous execution, where you launch a computation, it runs on the GPU whenever, your CPU continues to execute, and you say in the future, when this is done, do something. So think about all the C++ that you've learned so far. You can't do that operation. Normally C++ is very imperative, right? One operation after the other. But with std future, what you can do is you launch something asynchronously, and then you say, okay, you go execute and you come back whenever you're ready, and then you sit and continue to execute, and you sort of do a wait and say, when it's done, continue over here, and solve in one single program. So C++ has also been going through a revolution. How many of you code actively in C++? How many of you have written a course project in C++? Anybody here? Happy to see a few hands. This number is dwindling every time that we teach this course, but you know, C++ is a good language, not the best language necessarily, but very powerful language for performance. Some of the impacts of this advancement is that in C++, historically, when you write programs, you actually would be showing how to do things and not what to do. And so there's a question on using OpenMP, right? So this is a question, this is a scientific program written and accelerated in OpenMP. It's practically impossible to figure out what is happening here. But if you use modern C++ and use a function called stud transform reduce, that's actually what's being implemented over here. So again, with these advancements, your C++, I always get a question, you're saying, hey, this looks like Python, doesn't look like C++ anymore, right? That's true, right? But the power is that these algorithms that are implemented behind the scene are implemented by Ninja programmers with good compiler optimization so that you get very good performance. So from a programmer's perspective, you can get a lot more performance by using some of these functions. Okay, so I'm going to briefly talk about the algorithm library because that's important to build up towards the StudPar, which is my parallelism in C++. The algorithm library has been very powerful. It's been available since C++ 11, close to 15 years now. Very strong. It has built-in implementations for most common functions. How many of you have used the algorithms library? Pound include algorithms.h. Anybody who writes C++, I see one hand up, two hands up. Very good. So if you write C++ code, I strongly encourage you to see the algorithm library because it has commonly implemented functions for almost everything that you do. If you ever in C++ write a for loop, stop, go to the algorithms library and find the function. So you do a for loop with operation on a particular array, you're doing it wrong. Go to algorithms, right? So one of the best videos that I've seen, like I said, my deck is mostly a bunch of videos, right? I'm not going to show the video, but it's a link to a video. One of the best learning material for stud algorithms is this talk by Jonathan. He's one of the core contributors to C++. It's a beautifully laid out world map of the algorithms. So he does 105 algorithms in 100 minutes. So you can imagine, he doesn't talk very fast, right? So he's very nicely categorized all the algorithms, right? So he's categorized them into your algorithms on sets, your algorithms that operate on raw memory, algorithms that are used for queries, things that do permutations, your movers, and so on. So I'll just give you a brief, there's a link to this in the slide. I'll give you a brief sense for the kind of algorithms that exist in each partition, right? And again, if you're writing C++, chances are you've written a for loop on a vector or an array or a allocated thing to do the same thing. Go back, change your code, use algorithms. It's very powerful. Permutations examples include, dealing with heaps, sorting, one of the most common operation you do on sets of things, all kind of queries, right? Whether it's counting, accumulating, how many, all of, none of, searching, all of those are implemented. You just include pound algorithm.h, you do stud : something and pass it an STL and it just works. All kind of operations on sets, set difference, set union, set intersection. You can move, copy, you take one STL, you take another STL, you give it the pointer, you say move. Why is that powerful? Because depending on the CPU, depending on the caches, you've all learnt about tiling, right? The way that the algorithm gets implemented, your compiler may not be able to figure out that it can tile things well. However, if you call stud copy, for example, to copy from one to the other, the algorithm is implemented differently for different architectures. So it actually, the compiler queries what architecture you have. Do you have an AMD CPU, an Intel CPU, an ARM CPU? It knows what the cache sizes are and picks up the right implementation so that you get best performance. So the performance that you get by using stud algorithms is very powerful. So that's why I strongly encourage you to look at and use stud algorithms. All kinds of value modifiers, filling, generating, replacing, structural changes. I think you get the gist of it, right? So a very powerful algorithm. Finally, there's also, you can take any of these and say do this for n. Move n elements, move, copy n elements, so on and so forth. And you can also do queries and things like that. Again, just gives you a flavor. Remember, the rule is, if you're writing C++, you're trying to do parallel processing, you do a for something with an iterator, stop, go and see the algorithm library and you'll find something very powerful over there. Okay. Now, assuming that you're on stud algorithms, in C++ 17, what was introduced was this concept of an execution policy, where to a particular stud algorithm, you can specify what's called an execution policy and automatically it runs on the CPU or the GPU. As a programmer, you don't have to worry about whether you're running an heterogeneous system or is a CPU, is a GPU, is the NPU, is a QPU, Anybody know what a QPU is? Quantum. Who answered? You got it. Did you get a chocolate already? I can give you one more. It's okay. Trying to keep you guys awake. Thank you, sir. So, so execution policy is very powerful. So I'll talk a little bit about execution policy, and then I'm slowly marching towards how Python attracts a similar strategy, right? So with C++ execution policy, the idea basically is a specific algorithm can be vectorized or parallelized using a simple construct. Can somebody take a crack at the question, or I had answered the question, what's the difference between vector and parallel? Or to be more specific, what is the difference between SIMD and SIMT? SIMD, SIMT. Anybody, what does SIMD stand for? Anybody, have you guys heard SIMD? Single instruction, multiple data. What is SIMT? Multiple thread. Okay, very good. What do you think CUDA is? Is it SIMD or SIMT? MT, exactly. So they can all run independent of each other. They're going to all run the same instruction, but they're not necessarily going to run the same instruction at the same time. They all are going to run the same sequence of instructions, but in parallel and not necessarily in lockstep. That's the main difference, right? I haven't given you a chocolate, have I? I'll give you one. Okay, so again, the execution policy is specified as the first parameter to the algorithm, and then the GPU allocation, data movement, all of that is completely handled by the compiler. As a programmer, you don't have to worry about, is there a GPU, is there a CPU, who has memory, do I allocate memory here, do I move memory there? Very beautiful, very powerful construct. So a very nice simple example, you have a sort algorithm, you allocate an STL and you give it the two iterators, the begin and the end iterator, and you give it a compare function, compare by last name, so that's what it uses for sorting. To make it parallel, all you do is just add stood execution par in front, that's it. Nothing else, no CUDA underscore underscore device underscore underscore, none of it, no MLR compiler building, you don't have to do any of that. Right. All this is taken care of completely by a compliant C++ 17 execution policy compiler like NVCC, and it just generates and runs directly on the hardware. So there are a lot of, there are 4 options that you can specify. By default, the execution policy is sequential, where everything runs one after the other. If you don't specify execution policy, this is what is used. The second is called an unsequence or a vector execution, SIMD type of execution. You as a programmer have to guarantee that the operation is thread safe. That's something that's important, but the compiler is not going to check for it. But if the important thing is that if it runs on a piece of hardware that has a vector unit, it automatically vectorizes it. So you as a programmer don't have to do anything. Similarly with stood execution par, it automatically finds out if there is a GPU, it generates a parallel version. And then there's a combination of both. You can have both SIMD and SIMT. Actually, that's what happens in the NVIDIA GPU, where a few threads run in lockstep, but across SMs, they run without lockstep of each other. So that's a par, sec, unsec, both of which you can do. So I'm not going to go into this detail. There are a lot of nuances of using stood par. Again, you're trying to kind of breach a programming abstraction between a sequential program and a parallel program. So there are a lot of nuances that are involved in programming with stood par. But since that's not the focus of this class, I'm not going to really talk about it. It's a nice blog that talks about this in more detail. And this is constantly evolving, right? Like I said, enabling parallelism in C++, with literally every version, C++ 26 expected to come out next year, we are starting to get newer and newer constructs that enable great parallelism. Like for example, in C++ 26, there's an idea of a sender and a receiver. Right, so you write 2 threads, you say I'm the sender, I'm the receiver, and I just have to wait for a piece of data. So it's like a data flow that starts to get implemented. C++ looking more and more like a parallel algorithm. And this ironically is being driven by NVIDIA, who invented CUDA. Right, so it's very funny, right? Because they invented CUDA, they unleashed the world to write CUDA. Now it's becoming a little out of hand. So you try to come back to people and say, no, don't write all that complexity. Let's bring you back to a little bit more sane world. So this looks like the sane world that they aim to bring people back towards. But again, very powerful, very fast evolving. Okay, and the performance of this is real, right? So you can actually see. The performance of this is actually real, and it's not just some esoteric implementation that does not work in the real world. This is actually showing for the exact same piece of code with not a single line of change for different really large applications that are used in fluid dynamics, lattice Boltzmann simulations and multiple physics aerodynamic simulations. The performance gain that you get by running the same piece of code without a single line of modification on the CPU and GPU, right? Just by leveraging stood algorithm and then the parallel execution sequence. It's a very powerful paradigm, gives you great performance. You can see some of the numbers, right? Same thing run on the x86 CPU gets 7x gain on a GPU when compared to CPU with no change. So you don't have to write any new CUDA, no new changes, no compiler building. All this is taken care of by C++ itself. So the question then naturally comes to all those of you who didn't raise your hand saying that you write C++ regularly, you are Python programmers. What about Python? And Python is today, thanks to AI, one of the most popular languages to develop applications. So should we not tailor to them? Shouldn't we also be able to give Python programmers performance? The biggest challenge with Python is that Python by default, like C++ used to, or C++ still does, Python only executes one thread. Python knows one thread by default. The main Python thread is only a single thread. Python actually in language specification supports multi-threading like you do with C++, but when you write code like that, it looks like C++ and you don't want to write Python. You might as well write C++, more performant, right? So what do you do with this? There's been a lot of advancements towards enabling parallelism in Python, which is what I'll talk about in the next 45 minutes of my lecture, where there are multiple domain-specific languages that are evolving, PyTorch being a great example, but others like JAX, TensorFlow, all of these are evolving, enabling you to write similar to the idea of std_par, where you write the program like a sequential programmer, parallelism is automatically handled by the compiler. Fundamentally, that's the idea, right? You try to keep the programmer thinking like a sequential programmer. He or she should not worry about performance, should not worry about heterogeneity, but the compiler under the hood, many of which is multi-threaded and MLIR based, takes care of performance automatically. In fact, like I shown you earlier, all the vendor libraries earlier that were available only for C++ starting last year started to be available for Python as well. So all Python programmers can also directly target vendor libraries from programs, which is something that AI developers who write very common. All this is great, right? But what if you want real performance? Again, I'm the ninja programmer. I want to wear my ninja hat. I want to dig into the trenches. I want to get performance out of the GPU. I don't want to be the foreman in the top just giving instructions of how to run things, but I want to be able to dig and go. What are my options? Right? Can I not stay in the block-based land? Can I not stay in abstracted land? Do I have to write code like what I'd shown in CUDA? Is a big question that programmers who worried about performance started asking. And this resulted in this new abstraction, which is called the block level abstraction. So here's a very nice way to understand block level abstraction. So typically when you, let's say, do image processing, you're dealing with a matrix, which is an image in this case. So if you're writing a Python program, you're dealing with a tensor is like this, right? So in Python, you say you take two tensors and you add them. So you specify what's called a grid level programming model, where you are only doing bulk data operations on tensor to tensor, and all of the work of compiling that grid level operation down to the GPU, whether it be blocks and threads, is all done by the compiler. Right? MLIR compilers, great promise, we hope it gets there, it's not yet there. The other extreme is CUDA, where you literally are programming every pixel of that particular image. Where you're saying every pixel go and do something, or a group of pixels go and do something. And you specify in great detail what needs to be done. You specify how synchronization between the threads and across the threads actually has to happen. So your application or an application writer maps the data into everything. Starting a couple of years back, what people started to agree that this was not giving great performance, but this thing was too complicated. You saw the example of MATML, right? It's too complicated. So this resulted in what's called the block level programming model, where as an application writer, you understand how to take that particular matrix and, for example, tile it. Good example. Tiling is a very good example, right? Because remember that not all tiles might be even. Some tiles might be a little asynchronous. But only as an application programmer you understand, okay, there are some properties about this matrix that I can infer compiler will find it difficult to do these inferences because pointer aliasing becomes problematic, interprocedural analysis is not always available. So as a programmer, you do the blocking, and then the mapping from the block to the thread is completely left up to the compiler. Fantastic. It's exactly like abstraction of CUDA, except it's a very non-trivial abstraction of CUDA, right? Because CUDA deals with threads. CUDA knows only threads. So this is exactly an abstraction of CUDA, except that inside each block, I'll show you why the differences are there. You only program at a block level, and you don't, for example, worry about things like memory coalescing and things that's important to leave with CUDA. You'll see why the differences. But yes, in a very dumbified conceptual level, you can say, yeah, instead of programming on a thread, I can just do it on a block, but it's a little bit more different than that. I'll show you examples. Okay? Idea clear so far? Okay, wonderful. So Triton emerged as one of the popular block-based programming languages. Triton actually emerged out of OpenAI. How many of you have heard of OpenAI? Everybody? Good. I'm just trying to wake people up. I see some nodding faces, right? So Triton emerged from OpenAI as a block-based programming language. Again, coming back to the same issue that they were trying to use CUDA because they've spent trillions of dollars now on GPUs and they want to make sure that they use the damn thing. And so they started writing CUDA. It's very difficult to handle. So the main thing with Triton was the kernel is single-threaded. You're dealing with a block at a time. The difference here was that in CUDA, within, let's say for example, take this grid, which was, remember what that image that I showed you, right? In CUDA, you break the grid into a bunch of blocks and you break the blocks into a bunch of threads. And you as a programmer in the _ device _ I showed earlier are programming every thread. You say thread 0, 0 does this, thread 0, 1 does this. In Triton, what you're instead saying is, I don't program every thread, I say at the block level what I will actually do. When I say in block 1, 1, these are the operations. So therefore, like for example, in CUDA, what I can say is, some threads of mine will do something differently from others depending on the thread index. In Triton, you can't do that. You can only say everything inside a block is all I control. Like for example, in Triton, I can also, in CUDA, I can control the memory layout to make sure I get coalescing of memory accesses. In Triton, you as a programmer don't have control to those things. Only that can be done by the compiler. In Triton, I'll show you examples of code, it'll become a little more clear. But in Triton, the idea is you're programming at a block level and not at the thread level. And the mapping from the thread to the block, from the block to the thread is done completely by the compiler. So the idea of Triton germinated because GPU ninjas were hard to find. Ninjas are always hard to find by definition, right? They are stealth. So it's becoming very difficult to find and make people become GPU ninjas. And the idea was, as time went on, eventually your CUDA code caught up to the performance of Triton. But in some cases, you don't really need to wait. You don't want to wait for so much time. Let's take an example, right? Take OpenAI. They literally release a new model every 3 months. The time it takes to optimize a particular model is about 6 months. So if OpenAI were to wait for a model implemented in PyTorch to be implemented in, I don't know what they implemented, I'm just taking a guess, okay. If let's say they implemented something in PyTorch, they had to CUDAfy everything, it's going to take them another 6 months to release a model, by which time Gemini would release a new model, Anthropic would release a new model, and the world would have changed, right. So sometimes the development time is a very important factor. It's not just about performance always. In some cases, you can afford to give up some performance at the gained advantage of development time. I see some faces wondering, who the hell will do that? It happens, right? Because your metric sometimes is time to market. You want to make sure that the best, greatest model comes out fast, right? Like for example, again, OpenAI, fantastic example. ChatGPT released in 2022, 3 years ago, 2022 November. Time to market, right? Everybody had models around the corner, but ChatGPT released it first. They captured the market, $100 million active monthly users today, because first mover advantage, huge. So Triton becomes very useful when you don't get the performance that you can get, but development time is very important. CUDA can eventually catch up. There's another lower programming language called SAS, which is like writing assembly. I don't want to talk about that, but it's a trade-off between development time and performance. Okay. The other brilliance with Triton is that Triton is cross-platform. Remember I told you that CUDA was restricted to NVIDIA GPUs. Triton works both on NVIDIA GPUs and on AMD GPUs, and now on pretty much every hardware backend, including the hexagon backend you saw in the morning. And in fact, Triton is becoming so popular that Triton is becoming the language in which compilers for deep learning models emit code. Instead of emitting machine code, which is what normally compilers do, what compilers for deep learning today do is they either try to go and emit, they try to go and use the libraries like I told you, cuDNN, they find a match, or they emit Triton code. And then Triton under the hood gets compiled down using an MLIR compiler to the hardware. Triton is becoming very popular as a consequence. In fact, PyTorch uses Triton extensively for a lot of compilation. So a brief overview of Triton, and then I'm going to go into some code, show you some stuff about the trade-offs involved in Triton. Triton is both a language and a compiler. Right, so they understood from the grounds up that you cannot distinguish the compiler and the language because you are giving a lot of power to the compiler. Your tensors are defined in SRAM, modified like Torch. It looks like Python. I'll show you examples. It looks exactly like Python. The Triton compiler, interestingly, uses MLIR based code gen for backend. Right, so it's very powerful abstraction. MLIR, all the progressive lowering, multiple levels, semantic information, all the jazz I spoke about, all that is inside the Triton compiler. Some of the key advantages is that one of the biggest advantages is it's embedded in Python. So as a Python programmer, I don't have to worry about CUDA, which was C++ only. I don't have to worry about learning CUDA, C++ syntax, none of that was necessary. Though it's Pythonic, to the ninja-ish, no, it's no longer ninja, right? It's like ninja-ish programmer, you still get pointers. You'll see this as an example in my examples. Arjun will walk you through a bunch of it. You actually get pointers. So if you want to mess with things, the power is there. It's up to you to take it. So the power is still there. And because it's block based, the compiler does not have to worry about a grid, which is a much larger scope. The block is typically much smaller, and the compiler is much better at p-pole optimizations. Who can tell me what a p-pole optimization is? Somebody. What's a p-pole optimization? Have you guys heard of the p-pole optimization this week? Fantastic. Peephole optimization, as the name suggests, you have a small window to look into, right? It's a small peephole. So a block is a peephole when compared to a grid, which is much larger. So peephole optimizations work very well in the compiler, and Triton is a peephole optimization space. You can actually work very well at the block level. So let's go Triton. So what I'm going to do over the next few slides is I'm going to take a vector add example, and I'm going to convert from Torch code to Triton. Okay, we're going to look at code. Hopefully the fonts are large enough to be able to see on the monitors. Right, feel free to walk up to any monitor. Feel free to stop me and ask me. It's fairly important that you follow, because otherwise the tutorial section will become a little hard. So we're going to look at some code. Okay, okay, wonderful. Let's start. It's a very simple vector add. Right, we're going to do an add. Fairly simple. It's a function I've defined called underscore add, which just returns x plus y. Nothing complex there. We have a torch.randn, which generates 1024 elements. With a randn, you can say where it lives on the GPU. You can see that you say device equals CUDA. You don't even say device equals GPU. That's how popular CUDA is as a framework, right? Device equals CUDA. It means that these three are allocated on the GPU. Calls z equals underscore and x comma y. Calls the function, comes back. With me? Very simple function, right? Great. Let's convert this into Triton. Okay, a few things, I'll walk you through it. It's fairly simple. Let's again start from the function definition. I've added this new decorator called @triton.jit. So any function decorated with an @triton.jit. What does JIT stand for? Just in time compiler, right? So all Triton functions are JITted. First thing to remember. Okay, you are an @triton.jit. Now instead of passing your entire tensor, you started getting pointers. That's the first difference in this function. Earlier your underscore add just took the tensor x comma y. You started getting pointers. You start seeing these new calls to tl.arange, tl.load, tl.store, which are language extensions coming from Triton. The Triton lang you imported here as Triton.language as TL, right? You declared a bunch of offsets, tl.arange. basically you're manipulating within this block, you're manipulating 1024 entries of x comma y in parallel. Make sense? You load your x pointer, y pointer, z pointer into a pointers depending on the offset, right? You call a TL dot load where you actually are doing the load. You do the computation, you do a TL dot store. In your host code, which is what we call the launch code, you're still calling x equals torch.rand, y equals torch.rand, z equals. You define something called a grid, and to the kernel you pass a grid parameter as well. Okay, and here n is actually 1024. I didn't fix that. Here n is actually 1024, so ignore the n. So what you're doing here is you're defining what's called a grid. Here I'm only defining one grid. So a grid basically is just one block. The entire grid is just one block for simplicity, but each kernel deals with 1024 elements of that block. Okay, as a programmer, you are thinking all 1024 elements are going to be operated on in parallel, but you didn't write. I did not go to every single element and do a manipulation. Instead, I operated at the block level. Yeah, but in CUDA, what you'll end up doing is you'll do a thread index, right? You'll actually go to a thread index. You'll do a thread index dot x and thread index dot y. You'll find exactly thread index and say for that thread index, what do you have to do? Here, it looks very similar because it is just a vector add. When you go to a more complex, you'll see it in the afternoon. When you go to a little more complex kernel, it will make sense. It looks a lot like CUDA. I'll give you that. It does look a lot like CUDA, but some of the advantages, right? So, okay. For those of you who have written some CUDA, right, can you tell me the differences between what you see here and what you see from CUDA? How many of you have written any CUDA code before? Anybody here? 1, 2, Arjun 3. Okay, can you tell me what the differences you see here? Pretty low level compared to CUDA. So in CUDA, typically what you have to do is you have to do a CUDA mem copy, CUDA malloc, CUDA mem copy. Is any of that there? So in CUDA, what you actually do in the host is you tell in the host that this is, instead of doing malloc, there's a special function that CUDA exports called CUDA malloc. Well, no surprises as to what it does, right? So you do a CUDA malloc, where anything that you pass inside CUDA malloc gets allocated on the GPU. Okay, but you get a pointer on the CPU for that particular thing, and then you got to do a CUDA mem copy from device to host or from host to device. So you as a programmer are responsible to move data between host and device, but here none of that happens. The data moves automatically, there's no synchronization. Remember in CUDA when we did the hello world problem, we said you'll get hello world jumbled up all over, right? You get H, you get V, none of that is necessary, none of that can happen here. Each block executes as if it's running in sequence after another block, but they all happen in parallel. Synchronization is completely handled by the compiler. So from a programmer's perspective, it's very powerful, and from a programming perspective, it's very simple, and from an execution perspective, it's very powerful because you're giving these offsets and you're doing effectively loads and stores using the TL.load and store extension. Automatic memory coalescing and all the memory related optimizations can happen automatically. Any questions so far? We'll go into, I think Arjun, you're going to work through a similar example, right? Question on the back? Yes. Beautiful question. So the question is, let's say that here you called an add, you got a z, x, comma, y. And let's say that you call another operation after this, which is a subtract, where z is an input, right? Fantastic question. What happens? Let's first take the CUDA world. In the CUDA world, what happens is exactly what you said. You as a programmer are responsible to do a CUDA malloc, CUDA mem copy device to host before you call the add, CUDA mem copy host device, CUDA mem copy host to device before you call the add, device to host after the add. Yes. So here what actually happens is when you call a sequence of operations A, B, C, because these get jittered, automatically the operators get fused. So there is actually, so let's say you had an add here, you had a z as the output, and let's say you have a subtract under this with Z as an input, the kernel actually becomes a single kernel on execution and it never comes back to the host. So again, the power of the compiler, right? Fusion, because of the fact that the compiler knows that there's a data dependence, is taken care of fully by itself. In CUDA, the compiler doesn't know because you're doing pointers, it gives up, cannot do alias analysis. Here it's very powerful. There's another question that went up. Yes. Yeah.
If every you have the add and the subtraction and all implicitly gets joined together, if you want to call anything on the CPU in between,
You can't. You can't. It's like a single function call. It's just like CUDA, right? When you call a CUDA function in the middle, you can't get anything in the middle out. It's very clearly defined what goes in, what goes out. That explicit clarity is required for the compiler to do code gen. Otherwise, it cannot do code gen. Yeah? Okay. Wonderful. So that's the example. So this was a very simple example where I said, okay, it was a beautiful single thread block which had it was a single grid and the block had 1024 threads. It was very simple. I've just slightly extended the same problem to, instead of calling 1024 blocks, I have n elements and each kernel operates on n by 1024. Each kernel operates on 1024, but I have n by 1024 blocks totally. So the grid size is n, the block size, that is each kernel operates on 1024 elements. Therefore, I need to launch n by 1024 copies of this kernel. The extensions are fairly simple. It's a little bit of changes you have to do. You have to figure out what your program ID is. This is similar to those of you who have written CUDA. In CUDA, you used to get a thread ID. Now you get your block ID because you just are dealing with blocks. There's a new element that we have introduced here called an offset, where I can actually say, depending on certain parameters, only a subset of a particular block may get launched. Like for example, here if you're not an integral multiple of 1024, the last bit will be less than 1024. So the mask here specifies that your offset should be less than n, so that you don't load out of the offset, you don't do out of memory accesses. But otherwise, the extension from one thread block with 1024 elements to n thread blocks or a grid size of n is pretty straightforward. I'm going to let you stare at the code for a second, right? You can start from the launch code always. Right? The launch code is what simplifies understanding what is actually happening. Inside the kernel, you're passing the grid size, which is n. The grid size actually is here. The grid size was passed, but it was not actually being used. There, the grid size is necessary because that's what enables you to set the mask up, so that you don't do an out of bounds access. Okay, I'm going to give you a few minutes. Just stare at the code. Any questions? Pretty simple. You'll do more of this in the afternoon, right? So, but pretty simple extension to what we had. So this is brilliant, right? So we started from Python. We started from Python or PyTorch. We went to this very nicely, not so complex in my opinion, but to those of you seeing tried for the first time, could look a little complex. Those of you written CUDA, it's actually very simple. And then you run it, and then performance is the same. Like, why the hell did you teach me all this? Anybody wants to guess why? I already gave you the answer, by the way. 2 chocolates up for grabs. Synchronization overhead. No, sir, sorry. So what did I tell you that the compilers, modern compilers do? They either use libraries or, so libraries are hand-generated code, handwritten code, or they generate, am I going to keep this or somebody else? Triton code. So the Torch compiler actually generates Triton code. So such a pain, right? Because we did all this work to get good performance and the Torch compiler is already doing all this. So we don't have to do this. But this is a simple enough example that you can actually understand the code. Now we'll go to a little more complex functions. I initially had the code, I pulled it out. It's a little too complex to understand. I don't know if Arjun has more complex code than this in the afternoon for you to look at. He's smiling, so he's a little masochistic that way maybe, sadistic that way. But if you look at it, let's look at this graph, right? So this graph is actually showing what your Torch JIT, which is what you get as native Torch performance is achieved on the y-axis. So it shows GBPS, which is akin to performance with different sizes. Torch native, which is the Torch compiled code, which could generate Triton depending on certain parameters. The performance it achieves is under what is achieved when you do handwritten Triton. Right? And with different sizes, you can actually see that the Torch looks like Torch matches some particular stencil sizes which are integral multiples of 2. So you see a big boost then it tapers down because there's a lot of extra work you're doing. Let's say that you have a stencil size of 512 by 512, your array is 384 by 384, suddenly a lot of wasted work, right? That's probably what's happening here, but I'm just guessing. But Titan, you can write a nice kernel, much less complex than CUDA. If I wrote the CUDA curve, it will look on top. Actually, the CUDA curve comes up next. There's a nice example of that. But you can see that automatically for not all functions, more real world functions, not as simple as vector add, the Triton compiler is not able to match your handwritten code. And this is 10 lines of code. I think in CUDA this would be at least 50 if not 100 lines. This is softmax. What is softmax? Who knows what softmax is? Sorry? Activation. One chocolate for you maybe? Yeah, fair. Activation function, right? So the other one, the other one is actually a nice example where matmul that you see over here is written in Triton. The handwritten implementation is cuBLAS, which comes from NVIDIA. I showed you the library earlier. CUDA basic linear algebra solvers, cuBLAS. That's the blue line. The Triton code, which is the cuBLAS is closed source, so we don't know how much it is, but from practical experience, I can tell you matmul, you saw the example earlier. How many lines was that? 100 lines? 100 lines? It's 25 lines of Triton code. And you can see that the pink curve tracks the green curve very close, especially for larger sizes. Much, much simpler. And interestingly, going back to the question that gentleman asked, a beautiful question. What happens in cuBLAS when you do cuBLAS with matmul with the activation function, right? In this case, is a leaky relu. You call cuBLAS directly, but leaky relu you write in torch.nn or leaky relu. The compiler doesn't know anything about cuBLAS, so it's going to treat them as two independent kernels, and suddenly the dotted green line starts dipping because you have to go and call that kernel, and the compiler between them is going to come back to the CPU and go back. On the other hand, with Triton and leaky relu, both written in Triton, the compiler does a fusion and you don't come back to the CPU and the performance does not dip. So the pink dotted line, which you cannot see, is actually overlapping with the solid dotted line and you get the same performance. Leaky relu is actually a very simple function. The computational is a very simple operation. But because you came back to the CPU in the middle when you had to do cuBLAS plus torch leaky relu, it's a big problem. Well, when you write it in torch, think of it as you have to come back. More importantly, the kernel execution has to stop, data has to be moved back, the compiler generates code for all that, and then the next guy gets called. In Triton, what happens is the compiler knows that the matmul function, which is an act triton.jit kernel, and the leaky relu function has a data dependence, are going to execute one after the other. So it just stays on the GPU. So data never, so let's think of it this way, right? So let's say that this is the CPU and let's say this is the GPU, right? Let's take the example of cuBLAS plus torch NN, right? So you have the inputs, you send the inputs from here, cuBLAS runs here, right? Once cuBLAS is done, data comes back here, output has to come back here, right? Then it will send the same as the input to the leaky relu and then gets the output back. When you do the fusion, this step is avoided. You don't have to do any of that because the data just remains on the GPU. No, if it's completely in Triton, the kernels get fused and therefore the data does not have to come back. In this case, the torch NN leaky relu is a torch function, cuBLAS is a CUDA function, which is a black box. So you cannot fuse them together. You cannot generate code such that the output of the torch NN on the GPU, so the output of the cuBLAS remains on the GPU for torch NN to use it. In CUDA, from one kernel to the other, it's actually stateless. You cannot assume the data is still in the GPU. That's the problem. You have to come back to the CPU. And then send it, exactly. Well, the word learn is a little overloaded, let's not use that word. But depending on what the next step is, you have to make sure that the data is sent back to the GPU. I mean, you generate code for all this, but at a compiler stage, you cannot figure it out because you don't know what the cuBLAS output is. You have to be conservative as a compiler. Think of it that way. Good question. It's possible. If torch ends up generating Triton code, then yes. But if torch ends, remember torch compiler could also call Triton, could also call a library function, in which case it won't get fused. I'm not advocating to write everything in Triton, but writing in Triton gives you chances. If you wrote it in CUDA, there's no chance. I can tell you that. I can tell it that way. Even in fact, the irony is, if you wrote two CUDA functions, one for MACML and one for leaky yellow, and you executed them one after the other, the CUDA compiler cannot fuse them. Once the CUDA compiler sees a native kernel, the CUDA compiler does not do anything across kernels. No interpretation across kernels. I'd love to see a research paper from you doing that. Of course you can, yeah. It's a non-trivial problem though. Yeah. Correct. That's perfectly right. Yeah, so yeah, you cannot deal with that complexity easily, right? Unknown shapes, as morning was mentioned, right? That concept of dynamic shapes, very difficult to handle. So Triton doesn't have a magic silver bullet to deal with that. It has to be conservative. At the end of the day, for execution has to be correct. But in the practical world, even in the image processing world, in practical deployments, dynamic constructs are not used because very difficult to predict. So you cannot optimize. So you'll end up with performance that looks like this. Not even this. You want this, and you probably want higher than this. Yeah? So another question? Very nice. I'm happy to see questions. I like it. Okay. Like the rest of my slides, this is also evolving very quickly. Okay. So this graph is showing a trade-off between performance on the y-axis and productivity on the x-axis. On the right extreme is torch. CUDA is here, right? Triton was here, and in the last 12 months, all the other dots have come up, right? So there's been a new language. So SAS is a almost assembly level to CUDA, like I was saying. You can get much better performance. It's literally impossible to write SAS. Arjun, have you written any SAS? A little bit. So some of the crazy few only, right? Not everybody dares. But typically CUDA is where most people stop. But you can see there's a whole gamut of trade-offs between productivity and performance that has been coming up over the last years. So I'm going to spend the last 10 minutes of my lecture giving you a flavor of some of them and seeing what trade-offs they're actually achieving. Okay? Let's talk quickly about QTile. So QTile was introduced by NVIDIA. Very similar concept. In fact, the slides that I showed you about block-based came from NVIDIA, thanks to Stephen Jones, who's in his lecture who put the slide up. The idea is very similar. The main power with QTile is, in addition to being able to do block-based programming for Python, QTile also implements block-based programming for C++. When in C++, you could only deal with threads, in which case you are doing CUDA-like, but with C++ 17 and 20, you can actually deal with tensors. There's something called MD-span that is like a tensor, so you can actually make the code look like NumPy. But with Triton, with QTile, you can actually do block-based programming. If it doesn't make sense to you, don't worry about it. But essentially, the idea is very similar to what Triton has. You'll actually see the QTile Python matrix multiplier looks a lot like Triton. So CT dot, where's that fellow? CT.MMA, that's your matrix multiply and accumulate. Your partitions, zeros. It looks the code looks very similar. I just wanted to leave with one slide here where with QTile, again, similar to getting performance in the real world, the QTile execution comes very close to CUDA. So the last graph here, the graph here shows for Llama, Meta's Llama 3.1. How many of you have heard of the Llama models from Meta? Anybody here? What does it do? What does Llama do? Not the animal, the Meta models. Speak up, speak. Huh? Image generation. Okay. It's a language translator model. Does a bunch of other things now, right? So here you can actually see the performance difference between the eager flash-based execution, which is the flash attention execution, and a hand-tuned CUDA, right? It's 60% gap. So hand-tuned CUDA deployed in cuDNN, when you actually compile torch eager with cuDNN using something called TensorRT LLM or something like that, that's the performance you get. Those kernels are actually rewritten in QTile, probably 1/2 or 1/3 the number of lines, which means it's 3x faster to write. You get close to the performance. You're only 7% off. So if that's a trade-off that's interesting for you, it's a very fair thing to do. In fact, NVIDIA right now is considering Qtile to be a parallel path to your regular CUDA programs. So earlier CUDA programs followed this path of SIMT, and inside the binary they used to pack something called PTX, which is the virtual ISA. But now, in addition to PTX, they're also packing tile IR, and they're saying, okay, what I'm going to do is from generation to generation, I will pack the tile IR into my binary, and when you go to a new GPU, I will actually redo a lot of optimizations. And why can I do this? Because tile IR is an MLIR dialect. I have semantic information about the program. I know what the loop is. I know what the tensors are. So, given a new piece of hardware which has a new cache, which has new controller, new memory structure, I can actually generate much better code than if I use PTX, which is like LLVM. PTX looks exactly like LLVM. It's very low level SSA scalar only. Invented 2006, had a chance to change it again in 2025, this year. Okay. So Qtile very powerful, but this evolution continues. So Qtile, like I said, is very close to Triton. Helion is a new language that was released by Meta this year, about a few months back, if I remember. So on the left side, you can actually see how Meta looks at the abstraction level. Ignore the graph for now, I'm going to block it so you don't see it. But on the left side, you can actually see what the abstraction level Meta thinks of. PyTorch on top, PTX or CUDA right at the bottom, or PTX at the bottom, CUDA in the middle. Helion is between Triton and Torch. Right? I don't have code examples over here to talk about Helion. Again, you can find these easily online. But the idea with Helion is that if you use Helion with Facebook's Triton, you can actually get performance that's reasonably close to cuDNN. The last, look at the bright blue and the last teal colored bars. It's not too far away, and of course, significantly less complex to develop, significantly less complex to maintain, and therefore it's attractive when your focus is to constantly change the model, to explore new models. Your OpenAI, your Google, your Facebook, your Meta, whatever, you want to release new models. These are abstractions that enable you to get good performance. Okay, last slide. To conclude this section, of course, GPUs programmed with AI with CUDA really, in my opinion, enabled AI. AI was enabled by hardware, right? So don't believe anything else anybody tells you. But the alternate methods to program GPUs today exist and are evolving. MLIR has been at the root of enabling a lot of this. MLIR compilers, unfortunately, they have not evolved enough that you can replace everything with MLIR compilers. Libraries actually are packaged with hand-tuned implementations, and they actually work really well. So if you want to get performance, that's the first place to go and hit. And to close, the question actually that I'll leave you with is, I actually teach this as a last lecture to a CUDA class in IIT Madras, where they've spent the entire semester learning about CUDA, and I come and tell them CUDA is not a good thing to do. In fact, we are predicting that block-based programming abstraction is really evolving to the point that we think future programming of the GPU might actually be block-based and not thread-based, because it looks like a very good abstraction between NumPy or PyTorch at the top level and CUDA at the bottom level. So you get good performance, good enough performance. Most of them you actually match CUDA and significantly better productivity. Okay, so bunch of references. Like I said, most of these you will see are 2025 or 2023 and newer. Most of these references are videos. Some of the videos I strongly recommend. Video number 7, 105 STLs algos in an hour. Fantastic video. Many of them are fairly new in terms of the Triton, especially the Triton, the Helion and the Glue, Helion and Qtile, fairly new things, constantly evolving. So this brings me to a close. What we'll actually have after the break, which we will resume at 4 o'clock or a little earlier if you guys want, we can talk about it, is Arjun will come in and he'll give you a good flavor for Triton. You'll get a chance to write some Triton code, look at what the compiler transformation looks like. He'll introduce you to a new tool called Compiler Explorer. Have any of you used Compiler Explorer before? You've used it, fantastic, right? So Triton works in Compiler Explorer. You can actually see generated code. Here's a very nice set of things prepared. But before that, it's important that all of you check your email. Professor Indu has actually forwarded a link to a Google Colab notebook. Please make sure that you sign into Google Colab and you're able to access it. How many of you have already done this? No chocolates for that. I'm happy if you have. If you have not done it, please, before you come back to the tutorial that Arjun will run, please take some time and just sign in. Make sure that you're set up. That's the best way. That'll be most effective. Please ask lots of questions in the afternoon. like you've asked now, I'm very happy to have had a fairly interactive class. I hope I kept you all awake. The chocolates help now. If there's any questions, I'm happy to answer. If not, we'll take a break till 4. 4, do you want to come earlier or 4 o'clock is good? Too much information for 4? 4 o'clock? Okay. We have about hour and a half, maybe a little less. Last class one. Let's see. Okay. So we come back. So just to reiterate, Arjun's going to be here from 3:50. I'll also be here from 3:50. So if you need any help, it's not like class will not start at 3:50, so don't rush back. You have break till 4. If you want to come back, make sure you're set up before 4. That's great. Both of us will be here. We'll be able to help you. If you have any questions, I will hang around here just after class. Feel free to, you can ask now or feel free to. If not, I can see tea is ready outside. I'm excited. Thank you all very much. You've been a very good audience. Thank you. See you at 4.